All right, so yesterday we went over position versus time graphs, okay? We also went over a little bit of this formula. Okay, we went over a little bit of y equals m times x plus b. We're going to spend quite a bit of time on that today, and we're going to use it to extrapolate beyond the graphs that we build and calculate things beyond what the graph can show. Okay, so just a quick review. Y is the vertical value of any point on the line. Okay, what's m? Slope. Okay, what's x? Horizontal value of the same point on the line. Okay, and what's b? The value of y when x is 0. We call that the y-intercept. Okay, so it's important to know those things on every graph. Obviously, they represent something different. Okay, we're going to be using that quite a bit today. Okay, ringing a bell from yesterday. Okay, and then we did a bunch of stuff about position versus time graphs, which we'll talk a bit more about tomorrow when we do our lab on position versus time graphs. Okay, so first thing we want to look at here, okay, is if you can find the Google sheet that is about the book, number of sheets versus thickness. Okay, so if you open up your Google sheet, I can't remember if it's the first sheet or not. It's not. Okay, so if you go to the book thickness tab right here, okay, just click on that. That's the first one that we're going to do. Okay, so I've already put in the data for you, right? This is just a set of data that tells me the thickness of a book based on the number of pages the book has. Okay, that makes the number of pages the manipulated variable, and the thickness of the book the responding variable. Everybody okay with that idea? Right? The more pages, the thicker the book will be. Okay. So what we want to do here is we want to build a line graph, okay, actually a scatter plot with a best fit line on it of this data. Okay, how many people of you have built a graph using Google Sheets before? Okay, so not many of you, so kind of follow along, do what I do here, and you'll get your graph built. Okay, so the first thing we want to do is highlight all of the data, okay? Headings included. So just put your pointer in cell A1 and then click and drag until you highlight everything. Okay, so it'll turn slightly blue and look like that. Okay, because now we're telling Google Sheets, here's the data we want to graph. Okay, so then we're going to go to Insert. Okay, and you're going to go all the way down here to where it says Chart. And you're going to click Chart. Okay, when you do that, Google Sheets, well, this time anyway, picked the right kind of graph. Okay, it picked what we call a scatter plot, which basically just puts the points on the graph. Okay, it doesn't draw columns or lines or bars or anything like that. It just puts the points on the graph. Okay, everybody with me so far? All right, so is that graph reasonably formatted according to what we learned yesterday? Okay, like the y-axis is labeled thickness in millimeters. That's good. Okay, the number of sheets is on the x-axis, and when we say number, that's the units. So number is the units.
The number of sheets has to either start with 0 or have like some.
Nope, doesn't.
Oh, it doesn't.
Nope, it doesn't. Okay, this is going to look a little weird, but okay. Oh, actually, yes, it should. Hang on. It should have gone to 0, but it's okay. Actually, no, we'll be okay the way this is. It doesn't need to start at 0 for this graph, but I'll show you why in a second. Okay. All right. So for this graph here, okay, I think the only thing right now that I would change would probably be the title. I mean, that's what's on the graph, but it's not a great title. Okay. How do I change that title? Anybody know?
Customize.
Yeah. Okay. Actually, you can click on it directly even and change it there, or you can go to customize. Customize is best just because we're going to be doing a lot of things in the customize menu. Okay. So right now it says the title text is this. Okay. And I'm just going to put book thickness in there, just because thickness versus number of sheets is a bit, I don't know, obtuse maybe. It's just not very descriptive. Okay, so I'm going to say book thickness in millimeters versus the number of sheets. Okay, at least then we know we're talking about a book. All right, when you do that, it automatically updates the graph.
It might just be for me.
Are you what?
It might just be for me, but it cuts off the point, like
Yeah, it's a little bit cut off at the top.
Yeah.
Yeah, it's okay. It'll be fine. Okay, so now I've got that set up pretty well. Okay, I've got my graph there, but I need a couple of things on this graph. Okay, and the first thing I need is a line of best fit. Google calls it a trend line. Okay, I need a line that shows me what my points are doing. Otherwise, I can't use y equals mx plus b. I've got to have that line so that I can use y equals mx plus b. So the next thing we want to put on here is a trend line. So we're going to scroll down here a little ways in the customize menu, okay, to where it says series. Okay, so you're going to click on series, okay, and you'll see a bunch of these options here. You can play around with these if you want. Okay, I often make my points a little bit smaller when I'm making a graph. These are pretty big, but you can leave them right the way they are for now. Okay, and then I'm going to scroll down just a little bit further. Now that I've clicked that, I get these other options, and you can see that down below there's a checkbox beside trend line. Okay, if you click that, Google Sheets draws a line of best fit for you, which, believe it or not, is really nice. Okay, back in the day, you had to put a ruler on your paper and do your best to estimate what the trend of your line of your points was, and everybody would get a different slope for the same graph. Okay, so now that I've got that line on there, once I clicked trend line, a few more options show up underneath it. Okay, so I'm just going to scroll down to see those options. Okay, those options include what kind of line to draw. Linear is what we're going to use. Okay, and then it gives you some options about the line. I wouldn't change those, but this box here is important, where it says, what do you want to label the line? Okay, so right now it doesn't have any label on the line. It's just listed as none. Okay, so what we want to do, okay, is when we click on that, it says none, custom, or use equation. Which one do you think you want to use? Nope, you want to use equation, because now it's going to spit out y equals m times x plus b, but it's going to fill in some of the numbers for you. Okay, so if I go use equation, okay, it puts the equation of the line up here on the top of my graph. Okay, so what this has told me is that y equals 0.15 times x plus 5. So it tells me m and it tells me b. Okay, that's useful because now as long as I get an x value or a y value, I can calculate the other one using y equals mx plus b. Okay, so got this now. Now my graph is essentially complete. Okay, I've built the graph, it's got a good title, the axes are both labeled, okay, I've got a best fit line on there, and I've got the equation for that line. Okay? All right, everybody okay with that? Okay, so now I'm going to go back to my thing here. Okay, so you should have got a graph that looks basically like this. Now on this one here, mine actually went back to 0, but it's okay, it doesn't have to. Okay, so if yours, actually, here's what we'll do. We'll just copy the one that we have over. Okay, so now we've got this graph, and this graph has told us, okay, that our equation is y equals 0.15 times x plus 5. Okay? So that means that our slope is 0.15, agreed? 0.15 what?
Millimeters?
If I'm going to get the slope, remember that when I calculate slope, I'm going rise over run. So what units is the rise in? Millimeters. What unit is the runs in? Sheets. So what is the slope telling me? It's telling me the thickness of one sheet. That's the relationship between how many sheets and the thickness of the book, right? However many sheets there are multiplied by that number should give me the thickness of the book, agreed? Okay. Is that 100% true what I just said? If I take the number of sheets and multiply it by 0.15, I'll get the thickness of the book. It's not true. What's the y-intercept telling me?
Plus 5.
Well, it's telling me it's 5. It's telling me it's 5 millimeters when there are 0 sheets. Right? Remember, the y-intercept is what your y value is when x is 0. So what is the y-intercept telling me about this book? It's telling me how thick the cover is. Okay, do you see the kind of analysis we can do on a graph if we think about it? Okay, like so many people just try and memorize every graph they encounter. Okay, I'm not going to be able to memorize every graph I encounter, but I can look at this graph and reasonably determine what every part of that graph is representing and things the graph can tell me. Okay, I now know that the thickness of the cover of this book, okay, is 5 millimeters, and that the thickness of every page is 0.15 millimeters. Okay, that's pretty reasonable stuff to know. Would you agree? Okay, now using y equals mx plus b, so using this equation here, I want you to see if you can do these two questions here. We already did number 3. Okay, we already calculated the number of millimeters per sheet. That was 0.15. Okay, so here's my tip for you before you start. You're going to be using this equation. What you need to figure out is, are you solving for a y value or are you solving for an x value in these questions? Whichever one you're solving for, you're being given the other. Okay? I'll give you a couple minutes to see if you can solve those two things and then we'll walk through them together. All right, so in question number 1, it's wanting to know the number of sheets in a book that's 80 millimeters thick. What did they give me? They gave me y. Okay? How do I know that? Because they gave me a number in millimeters, and millimeters are on the y-axis. Okay? So that's my first step. I got to look at what I'm given. Okay? Write down my given, same as I would in any problem. Okay? And figure out what does that represent. That represents the thickness of the book, which is a y value. So number 1 is asking me to calculate an x value. So I've got to take y equals m times x plus b, and I've got to solve for x. What do I move first? B. Okay, so I subtract b from both sides. Okay, so y minus b equals m times x. Then what do I do? Divide by m. Right. Okay, so now I'm solving for x. Now I can plug in my numbers. So 80 millimeters is my y value minus what? 5. Yeah, that's what b is. Okay, so 80 minus 5, and then divide that by 0.15, which was our slope. Okay, so what we've got here is millimeters divided by millimeters per sheet. What am I going to be left with? Sheets. Yeah, that's what I'm looking for, so that's good. Okay, so I'm going to have 75 divided by 0.15. Sorry, I forgot to fire up my calculator. What does that come up to? 500? Okay, 500 sheets. Pretty straightforward? Okay. Now, question number 2 tells us how many pages / sheets there are in this book. Okay, so they gave me y or x. They gave me x. They want me to calculate. Okay, is that easier? Yeah, because I don't have to manipulate the equation. Okay, so all I have to do is go y equals 0.15 times 805 plus 5. Okay, and I'll have my thickness of the book there. So 0.15 times 805 plus 5. Okay, so that book is going to be just about 13 centimeters thick. Okay. War and Peace. It's going to be a thick book. Okay, 13 centimeters is a very, very thick book. Okay, these are thick pages. All right, everybody with me on that? Okay, is that terribly difficult?
No.
The algebra is not hard. Okay, the trickiest part is building the graph and then figuring out what's on each axis. Okay, all right. So next one I would like you guys to do is the graph of diameter versus circumference. So that'll be under circles graph. Right here, so the first tab. Okay, so in this one, the manipulated variable is the diameter, the responding variable is the circumference. Okay, I want you to build this graph. Okay, put the best fit line on there, get the equation, same as we did before. I'll give you a few minutes to do that. Okay, but before you start, I want a prediction. What is the slope of this graph going to be?
3.14.
Yep. I mean, what's the relationship between diameter and circumference? Pi. Okay? So, yeah, hopefully, if you do this right, you should get a slope that's somewhere around 3.1, 3.14, or something like that. Okay? So I'll give you a few minutes to build the graph, okay? And then I'll build it and we'll go over the questions related to it. Okay? All right, so let's quickly build the graph here, guys. So we just highlight everything. Okay, insert chart. Okay, it luckily again picks the right kind of chart. It picks a scatter plot. In the event that it doesn't pick the right kind of graph, because this happens from time to time, okay, you just go here to chart type in the setup menu. Okay, just click on it. It's a drop-down menu. Okay, and you got all kinds of choices there, but we always use the scatter plot option. Okay. So that's what we want, that's what it picked. Okay, gonna go to customize and probably go to chart axis and titles and change that. Okay, I don't know, circles graph. Okay, and then, okay, we'll go to series. Okay, it looks like everything is okay there in terms of units and labels and everything. Okay, so we're going to go to series and we are going to scroll down until we can get the trend line box. We'll click it. Okay, then we'll scroll down a little bit further to where it says label. Click on that. Use equation. Okay, boom, we got our graph all built and ready to go. Okay, did we get about the right slope? Yeah, I got 3.1. It rounds it off. It's probably closer to 3.14, but okay, that's what we'll leave it at for right now. Are we ready to do y equals mx plus b for that graph now? Okay, so it's all built. Okay, now we can just go to y equals mx plus b. So here's what I would like you to do. Okay, using the graph that you built there. Okay, I would like you to calculate 1 and 2. Is that y-intercept very, very small?
Yes.
Should it be?
Yes.
What should it be in a perfect world? It should be 0. In a perfect world, that number would be 0 because a circle with a diameter of 0 should have a circumference of 0. Okay, that is a very small number. There's always going to be a little bit of error. Okay, when you're plotting points, could be whoever measured the diameter or the circumference or whatever. Okay, so give you a few minutes on that, and then we'll go through those two. All right, let's have a look at these two questions here. So we're looking for the circumference of the circle. Are we looking for y or x? Looking for y. Circumference is on the y-axis. Okay, so for question number 1, we're looking for y. Okay, we know that the slope is 3.1. Okay, and we're multiplying that by the diameter we were given because that's an x value. So 0.88 meters plus 0.149 was the y-intercept we got. Okay, so not the most accurate, but we'll go for it. 3.1 times 0.88, okay, plus 0.149 tells me that the circumference of that circle would be 2.887, or 2.877, sorry, meters. Big circle. Okay. Everybody all right with that? Okay, and then the second one, they're telling us the circumference, so they're giving us y, okay, they're giving us y, and they're asking us to solve for x. Okay, so that means then that I have to manipulate the equation, so y equals m times x plus b, right? So to manipulate for x, I'm going to subtract b from both sides, and then I'm going to divide by m, and that will leave me with x. So I'll have 41.5 meters, that is a really big circle, okay, minus 0.149, which is really small by comparison, okay, and then I'm going to divide that by the slope that I had, 3.1, right, and that should give me my diameter. So 41.5 minus 0.149. Now, here's something you have to be mindful of. You can't just type this all in a row. Why not?
Because it'll do 1.49 divided by 3.1, and it will then take that away from 3.1.
Right. Your calculator defaults and is programmed to do order of operations. So if I just type this in like this, as Kessler said, your calculator is going to go 0.149 divided by 3.1, and then it's going to subtract that from 41.5. Is that the same as what we want it to do? Okay, so just be mindful of that. It's going to come up on a lot of formulas that we do. Okay, if you have an addition subtraction operation on the top, you're going to need to bracket it. Okay, so I'm going to have I'm going to need to bracket it. 41.5. Okay, minus 0.149, and then divide that by the bottom. Okay, or just do one and then the other. Right, so I should get a diameter there of 13.3 meters. Okay, everybody all right with that one? If I did it the other way, okay, if I did it the wrong way, like we had said, if you let your calculator do its thing and just went 41.5 minus 0.149 and then divided by 3.1, okay, we get a much different answer, right? Here's what you have to understand about physics. If an answer doesn't make sense, it's wrong. Physics always works. That's the beauty of physics. Okay? So, if I have a circle with a circumference of 41.5, it definitely can't have a diameter of 41.4. Agreed?
Yeah.
Okay, so always check your answer to make sure that it makes sense. Okay, that's the best way to check in case you've accidentally done some algebra or some math wrong. Okay, I tell this to my physics guys all the time. I ask them a question on one of their unit exams about acceleration due to gravity on Earth, and I make them calculate it in a different way. And if they do it wrong, they get a acceleration due to gravity that would be equivalent to standing on the event horizon of a black hole where you would be crushed. Okay, and they'll leave that answer. And I just say to them, like, why would you leave that answer? I asked you for acceleration due to gravity near the Earth. What number should you have gotten? 9.81. Then why did you tell me it was 1.8 times 10 to the 25? That answer makes no sense, but you left it there. Okay? Always check your answer, because I'm never going to be mean and have like a trick question where the answer doesn't make sense. Okay? The answer should always make sense within the context of reality. Okay? Does that sort of make sense to everybody?
That's Paul seated on the biology exam with the, what was that, I can't remember, like cytoskeleton or something?
Well, no, that question makes total sense. I just never taught you the cytoskeleton and forgot to take the question off. The question itself is totally valid, and the answer is correct. I just never taught it and forgot to take it off the test. Okay, let's have you guys try the next one here. Okay, so this one here is an experiment on a rubber band. Okay, so they're going to pick a bunch of distances, okay, and stretch the rubber band to those distances while measuring how much force is required to stretch it that far. Okay, so that means that the length of the rubber band is the manipulated variable, and the force is the responding variable. Okay, so I'd like you to build that graph and then answer those questions. Okay, and then we'll go through them together here in a little bit.
This isn't good.
Okay, well, let's walk through this one here. So the first one's wanting to know how long the rubber band will be if it's exposed to 15 newtons worth of force. Am I looking for y or x for number one? Looking for y, because length is on the y-axis. So don't have to do any manipulating, just have to plug in numbers. So that's going to be 2 times 15 newtons plus 6.5 centimeters. Okay, so that's going to be 36.5 centimeters, if my mental math is okay on that one. Everyone all right with that? Okay. What force is needed to stretch the band to 18.7? That should be centimeters. What do we need to do there? Solve for y or x? Solve for x. We're looking for force. Okay, so y equals m times x plus b. Okay, we're going to subtract b from both sides, divide by m. That'll give us x. So we will have then the 18.7 minus 6.5, okay, divided by 2. Okay, so 6.1 newtons would be about how much force we would need. Okay? How long is the rubber band when it's not stretched? 6.5 centimeters. Okay? All right, last thing. How many newtons do you need to stretch this thing 1 centimeter?
Like, stretch it a centimeter?
Yeah, it's stretching at how many newtons for every centimeter? Half. Half a newton per centimeter. How'd you figure that out?
Well, because, the length of band goes up to every newton that you stretch it, meaning if you stretch it 1, it'll go up 2, so to make it stretch 1, you need half.
Right, okay? Our slope is 2 centimeters per newton, okay? So that would mean 2 centimeters over 1 newton. So if I want to know how many newtons to stretch it 1 more centimeter, that would be the inverse of this, okay? 1 newton over 2 centimeters. So that would be 0.5 newtons per centimeter. Okay? All right, is this making some sense? Okay, is the slope on every graph represent something different? Yeah. Is it very hard to figure out?
No.
No, not really. Okay. All I think the next one is the one that's got more than one graph on it, right? No. Okay, let's do the single position versus time, then we've got a multiple one. Yeah, okay. So, this is the kind of graph we were talking about yesterday. So, in your data, oh, it's not even on there. All right, let's do the plant growth one instead. Then we'll do the position versus time graph with multiple runs. Okay, so I want you to graph the growth of the plant here. Time in weeks, height in meters. Okay, then we'll answer the questions about that, and then we'll move on to how do we plot it if we have more than one run. Okay, so if we build that plant growth graph, it should look something like this. We're getting a slope there. How quickly does this plant grow?
0.429 meters a week.
Right, okay? The rate of growth of this plant is the slope of this graph, and it is 0.0429 meters per week. So that's 4.5 centimeters per week, okay? And then it's telling us that the initial height of the plant was what?
0.23.
Yeah, 0.22, according to my line. Right, my y-intercept says that the initial height of the plant was 0.22, even though my data says 0.23. Is that okay that those two numbers don't agree? Yes, your best fit line is an average of all of your points. Okay, so the purpose of this graph is to illustrate this really important thing. All of these points, are any of them directly on the line? No. Okay, in fact, if I do this, if I go back into that customize menu, okay, and I make those points smaller, series, there we go. Okay, they're now quite obviously not on the line. Would you agree? Does a plant grow perfectly uniformly all the time?
No.
It doesn't. Okay, so all that best fit line and all any best fit line ever tries to do is basically take an average of all of the points that you plot. This was the challenge when you had to do these by hand. You basically had to make a judgment call. Every time you had a whole bunch of points, you put the ruler on the page and just kept moving around until you're like, yeah, that's good. And I'll draw that line. Okay, that was literally how you had to do it. You had to go, I think that follows the points pretty well, but no two people would ever draw the same line. Okay, at least with the computer doing it, it's putting in all your values and then actually calculating what's the best slope to have here given these points. Okay, so it's much more accurate and, nicely, everyone gets the same number if they're using the same data. Okay, all right, is that sort of making sense? Okay, that's the one I really wanted to use to show you that these points are not on your line. Okay, rarely is a point ever perfectly centered on your best fit line. That means you cannot use the values of individual points if you're trying to calculate anything about the line. Okay, you have to use numbers that are actually on the line, not points that you have plotted. Okay, because in all likelihood, the points you have plotted are not on your best fit line. Okay, all right. Now, next thing we want to look at here is the one that says multiple run graph. Okay, so I want everyone to go there because this is going to be more like what we're going to be doing tomorrow with our position versus time lab with the carts. Okay, so in this experiment, which, like I say, is just like what we're going to do tomorrow. Okay, is it okay to put the 3 different carts on the same graph? It absolutely is. Okay? We are going to be doing an experiment where they are all going to be timed for the same amount of time. On this experiment, it's only 5 seconds. Tomorrow it'll be like 30 or 40. Okay? But in this case, they're all being timed for the same amount of time. So it is absolutely appropriate to put them all on the same graph. Do I want each cart to have its own best fit line?
Yes.
Yes, I'm not trying to compare the carts. I'm trying to compare the data for each cart. Okay, so what I want is each cart to have its own line of best fit. All right, so when I'm building a graph, okay, and I'm going to have multiple essentially things on the y-axis, but only one singular x-axis, I need to make sure that the first column is what goes on the x-axis. Okay, Google Sheets will always throw everything else on the y by default, and that's what we want anyway. Okay, so what we want to do is same thing we did in the other ones here. Okay, we'll highlight all of our data. Okay, and then insert the chart, same as you did before. All right, here's where Google starts to not get things right. Is this the kind of graph I want?
No.
No, absolutely not. This is useless. Okay, so I've got to go over here to setup where it says chart type. And right now it says column chart. I don't want that. So I'm going to click on that and I'm going to scroll down to what kind? Scattered. Okay, that's better. Now I can clearly see the trend of each cart. Okay, one of them has yellow dots, one has red, one has blue. Okay, so I've got that. Okay, I'm going to make that a little bit bigger so it's easier to see. All right. What should I put on here next? How about okay, I'm going to put a trend line on for each card, but before that, how about a better title? Because that title's terrible. Okay, that's a completely meaningless title. Okay, so that's the first thing I want to change. Okay, I'm probably just going to call this position versus time graph. Position versus time for 3 carts. That's a lot more descriptive than what was on there before. Okay, something else that sometimes happens. What else is missing from this graph?
The title for the y-axis.
Yeah, there's no label on the y-axis. When you have more than one run, Google doesn't know what to label it. So you're going to have to tell it. Okay, so I'm going to have to go to Customize and go to Chart Axis and Titles. And right here where it says Title Text, where it says Chart Title, you're going to scroll down. Chart Title, and you're going to go Vertical Axis Title. Okay, and then you just type in, what's on that axis? Position in meters. Okay, so now that's on there. Graph's starting to look a bit better. As you guys said, the next thing that needs to go on there are the trend lines. Okay, plural, because we want one for each cart. Okay, so I'm just going to scroll down, same as I did before. Okay, there is a spot somewhere in here where it says apply. Okay, it says apply to all series. That's checked by default, so you won't usually have to do anything with that. Okay, that means it's going to do it for each cart. Okay, so we're going to scroll down, okay, to trend line again. All right, I clearly got 3 separate lines, one for each cart. They all need, however, a what? An equation. All right, so now I've got y equals mx plus b for each one of the carts. Okay, graph is complete. Okay, so let me ask you a couple of questions here. What's the initial position of cart 3?
0.
0.0381 meters. How do we know that? Is that the y-intercept for cart 3? And would the y-intercept on this graph be your position at time 0? Then it would be your initial position. Okay, that's exactly the kind of analysis I would ask you to do. Okay, interpretation of that graph. What's the velocity of cart 2? .01 meters per second. How did you know that?
Because that's the slope.
Okay, because that's the slope. And on this graph, if I calculate the slope, okay, so I've got my position versus time graph, okay, if I calculate the slope, I'm going final position minus initial position. What's on the x-axis? Time. Does that calculate, if I go displacement divided by time, does that calculate velocity? So the slope on this graph is the velocity of the cart. Okay, I don't have to memorize that. It took me like 10 seconds to figure it out. I just looked at what's on my y-axis, what's on my x-axis, what would I get if I did a slope calculation? Okay, I would get meters per second. That must mean it represents velocity.
Don't forget the positive, because you're asking for velocity.
Yeah, it would be positive. Yes, absolutely. You're right. Okay, it would be positive 2.01, okay, because velocity is a vector quantity. Okay, everybody with me so far? Okay, so this is the part you really want to make a note of. You're going to have a graph that looks very much like this tomorrow in your lab that you're going to have to do exactly what I'm about to ask you to do as the analysis. So basically, we're walking through how to do the analysis for tomorrow's lab right now. Okay, so this is like freebie marks, okay, for tomorrow's lab. Okay, so that's our graph. I want you to answer those three questions. Okay, velocity of each cart. That'll be easy because we kind of talked about that already. Okay, I want you to calculate the position of each cart after 12 seconds and how long it would take each cart to reach 50 meters. People have. Okay, remember when we had the Avogadro's number? Okay, that was a number in scientific notation, right? 6.02 times 10 to the 23. We use scientific notation a lot, okay, in physics and chemistry and things like that. Okay, what this means is this number multiplied by 10 times 10 times 10 times 10, 23 times. Okay, so when I give you this number here, 9.52 times 10 to the minus 3, okay, I'm saying this, 9.52 times 10 to the minus 3. Okay, this number here tells me how many spots I need to move the decimal to get the actual number. Now, you don't actually have to put in the real number. You can just put in that number in your calculator. Just go 9.52 negative 3, just like you'd put in Avogadro's number. Okay, but what this number really is if I was doing Avogadro's number, I know that this is a big number, right? Because the exponent is positive. So I would move the decimal this way 23 times, and then I would have the actual number. Okay, if I have this means the number is a decimal. That means I move the decimal this way. So this number is actually 0.00952. Okay, so that exponent that's on the 10 basically tells you here's how many spots to move the decimal, and if it's positive, you move the decimal to the right. If it's negative, you move the decimal to the left. Okay, so if something's 10 to the minus something, it's a decimal. It's a small number. If it's 10 to a positive exponent, then it's a big number. Okay, everybody follow me there? Okay. All right, well, let's have a look at question number 1, because do we actually have to do any calculating for number 1?
No.
No. What's the velocity for cart 1?
1.38.
Positive 1.38 meters per second. We already asked about number 2, it's 2.01, positive 2.01 meters per second. And for cart 3, it's 3.39, positive 3.39 meters per second. Okay, how many people are done number 2? Okay, let's look at number 2. On number 2, are we looking for y or x? We're looking for y. Position is on the y-axis. Okay, so for cart number 1, so we'll do that in blue. Okay, y equals 1.38 times 12 seconds. Are they all going to be times 12 seconds? Yeah. Okay, plus 0.00952. Okay, and that'll give me where cart number 1 is. So 1.38 times 12 plus 0.0, and it was positive, right? There. It was. Okay. 0.00952. All right, so it'll be at a position of 16.57 meters, positive. Okay, and then for cart number 2, okay, y is going to equal 2.01 times 12, okay, plus negative 0.0524. Is it okay if the y-intercept comes out negative? Yeah, it just means it actually started behind all the others and behind whatever we denoted to be 0. Okay, that's fine. It happens sometimes. Okay, so 2.01 times 12 plus negative 0.0524. Okay, so that one will be at 24.07 meters, positive 24.07 meters. Okay, and then for the last one, okay, y is going to equal 3.39 times 12 plus 0.0381. Okay, so it's going to be at a final position of 40.72 positive. Okay, do those numbers make sense? Does it make sense that the fastest cart should go the furthest?
Yes.
Yes, absolutely, in the same amount of time, yeah. Okay, those answers make total sense. How many people are done number 3? Okay, I'm gonna give you a couple minutes to catch up. If you're not done number 3, get number 3 done. It's the same calculation all the way through. You're doing it just for each cart. Okay, I'll give you a couple minutes on that and then we'll finish that one up. Okay, for cart number 1, we're gonna solve for x. Okay, x is always gonna be, okay, y minus b over m. Okay, it's gonna be the same manipulation all the way through. So for the blue cart, that's going to be 50 meters, because they gave me the y value, minus 0.00952, okay, divided by 1.38. Okay, should it take this cart a long time?
Yes.
Yes, because this cart is the slowest. Okay, so 50 minus 0.00952 divided by 1.38. Okay, so it's going to take this cart 36.22 seconds. Okay, for cart number 2, okay, we're going to solve for x. That's going to be 50 minus negative 0.0524 divided by 2.01. So 50 plus 0.0524 divided by 2.01. Okay, so that cart, that makes sense. It's faster. It should take less time to get to 50 meters, and it does, 24.9 seconds. Okay, and then for the yellow cart, which we know is our fastest, okay, x is going to equal 50 minus 0.0381 divided by 3.39. Okay, this cart should take the least amount of time, so 50 minus 0.0381, okay, divided by 3.39. It does take the least amount of time, 14.74 seconds. Okay, those 3 things are exactly what I'm going to ask you in your analysis for tomorrow's lab. Tomorrow's lab is strictly about position versus time graphs, what can we get from them, and using y equals mx plus b. Okay, that's what we're going to be looking at tomorrow in the lab. Okay, if I can get you 2, please sign out of those computers. Okay, bring them up. Look at your computer. If it's got a piece of blue masking tape on it, it needs to go in backwards. Okay, that means if it's got blue masking tape on it, it means that the charging port with the light doesn't work anymore. You just need to flip it around and put them in the other way. Okay?